trajectories, completing what we have to say about inverse kinematics. So very briefly, why do we discuss trajectories? We'll see this notion of interpolation. Probably you heard about this before, but good to revise. Then we'll talk about trajectories at joint space and at the end effector space. First talk about position, then about position and orientation together. So very quick recap. Again and again, I insist on reminding you forward kinematics is I know the joint coordinates and I'm calculating where is the end effector. While for inverse kinematics, I have a target pose and I want to calculate the joint coordinates to read that pose. Right? So where we are on the grand scheme, we have talked about transformations, forward kinematics, velocities, and we talked about inverse kinematics last week, and today we'll complete it. So why do we talk about trajectories? Right? We know we can control where the end effector will be. We can calculate joint coordinates for that. What's the deal with trajectories? So I have a small video here demonstrating like a very simple scenario where we have basically a robot that needs to perform a task, drill a hole on a specific piece, and obviously it has to result in a certain shape. This is a circle, could be any kind of shape, right? So we want to control the end effector, not just to go to a certain pose, but to do that continuously, to follow a certain path so that it can accomplish different tasks, like drilling, or in this case also welding in the second example. Right? And here we see that we don't only care about where the end effector will be, but also how it will be oriented. Right? For the drilling, we had to have a certain orientation where we kept the drill perpendicular to the surface. Let's say here, for this, if this is gluing or welding or whatever it is, again we have to be perpendicular to the two surfaces, or have a certain orientation around this surface so that we can perform the task properly. Like in this case, gluing. Right? We cannot glue in any orientation, or we cannot weld in any orientation. So we have to make sure both the position and the orientation somehow follow a specific trajectory. Right? So very simple example, I guess this demonstrates. This can be for any kind of operation of the robot. All right. So why trajectories? We don't only care about where the end effector will go, but also what path will it reach. And this is, as I demonstrated in the video, useful for tasks, for welding, drilling, whatever. But it can also be useful when avoiding obstacles. Like we might want to calculate a certain path that the robot has to follow so that it avoids certain obstacles in the environment. Right? And if we are able to follow specific paths, then we can make sure also to avoid certain tricky configuration for the robot, as we talked in the Jacobian lab, where we talked about singularities, where the robot loses degrees of freedom and so on. Right? So if we have this possibility, we can make sure we are away from singularities, for instance. So one key concept that we need for when talking about trajectories is the concept of interpolation. So we'll see a little bit of the math behind it, very simple math. And we'll start talking about linear interpolation. Like, what does interpolation mean? When you see this figure as well, what do you get? Did you ever hear this concept before? Yeah. In what context, and what do you do with interpolation?
I have in the context of animations.
Animations. All right. So what does?
I don't know. Let's say a ball here and you want to move it here. If you just in the animation, if you just change its location, it will just teleport in a second. Yeah. So you can use interpolation to have intermediate steps.
a smooth transition from the initial position of the object to the final one. Right? Okay. So that's what interpolation is. Actually, what does it mean? I have an initial value. Here is QS, Q starting, at a certain moment in time, and then I have an ending value, right, for the same value, and I want to transition from the starting to the ending value, in this case using a line. That's why it's called the linear interpolation, right? So how do I go from here to here following a line? Basically this would be an equation, a line equation. Anyone would know what would be the form of the equation? So what is the line equation? Why? Sorry? Actually, this would be my Q, okay, which would be a function of time.
A times plus B.
A times Q, T plus B. Right? This would be a line. And I need to find these two coefficients so that the line passes from these 2 points, basically. Right? Because 2 points define a line. Basically. I can save this equation for these 2 points. Basically, we have two equations for different Q. For QS equals A times TS plus B, and the same for Q end and T end. I have two equations, two unknowns. I can solve this and figure out what are the values. Right? Very simple. Basically, in a general form, it would have this this form. Right? So here I have T hidden in here, T, QS, QE, and T here. And you can see that basically when T equals TS, what do I get? I get this part here, TS minus TS, it will be 0, right? So it will be 1 minus 0 times QS, so QS, plus 0 times QE. So I will have, when T equals TS, I will have Q of T of S equals to QS. Right? So I will have the starting value. When T equals T end, I'll have T end minus TS up here, so this will be TE minus TS over TE minus TS, so 1. Right, so it will be 1 minus 1, this will be 0 times QS, 0, plus 1 times QE equals to QE. Right? This is not in the same form as this one, but we can, if we isolate T, we can write in this form. And we can figure out what is A and B, but it's convenient for our use case to have it in this form. Right? All right. To make things a little bit more simple, we will define a new function called S, which will be our interpolator, and S will be basically the part that repeats there. Right? So we have this S. I'll write it here. I think we'll need it in a second. S of T will be T minus TS, T minus TS. Alright? Where basically when T goes from T start to T end, S goes from 0 to 1. Right? That's what I have here. For T from TS to TE, S is from 0 to 1. And when TS, this will be 0, when TE, this will be 1. And it's a line as well. Alright, so basically our equation up, I can write it as a function of S of T, okay, where QT will again vary from Q of time, will vary from Q starting to Q ending, where S will vary from 0 to 1. It's a little bit dense here, but basically I'm writing this like this: Q of time 1 minus S of time, Q starting plus S of time, Q ending. All right. Now, yeah, I can change the slope. So, because this is basically a line equation, written a bit differently. I forgot to write it here. So it's in this form. I can change the slope by changing this value of a, right? And I can make basically the interpolation go faster or slower, but again it will reach basically the same ending value. It's just going to happen at different ending time. I can do this by changing the difference between time, starting time and ending time, basically, right? So if I squeeze these two closer together, then I will have a quicker transition. All right? Good. Now, how do we use this when talking about trajectories? We'll first talk about joint trajectories, right? So a typical use case would be, I don't know, I have an initial pose for my robot, let's say here, and I have a final pose for my robot here. Maybe let me draw a robot as well. Alright, and then let's do another color for the ending pose. Still here. Right, starting, ending. PS and pose. Right, the simple thing that I could do is basically to transition from this pose to this pose would be calculate the joint coordinates for this pose. How can I do that? If I have a target pose and I know my forward kinematics, what do I need to use in order to calculate the initial, inverse kinematics? So through, let's do it, PS I kine will give me QS1, 2. In this case I have only two joints, so the starting joints for this pose. And from this pose, again, I kine, I'll have Q ending 1, Q ending 2, right? The two joint coordinates for this pose. And then interpolate between them. So calculate the transition from QS1 to QS2, QN1, and a transition from QS2 QN2. Right, calculate this transition using interpolation. So basically what we're doing here, this is my starting value, this is my ending value. I can interpolate separately and then figure out what's the transition that takes me from this pose to that pose. Right? And we can interpolate them separately because they're basically independent. Like we assume, and it's a good assumption that each joint can move independently. Right? Okay. How do I interpolate? I interpolate using this form that we saw there, where instead of just Q, I have Q1 or Q2. And Q starting 1, Q ending 1, Q starting 2, Q ending 2. That's on the screen. Great. Now, we have different possibilities here. We can interpolate over the same time period, both joints, right? So let's say the same starting and ending times, right? They both start at the same time and end at the same time, which would look something like this. I have Q1S, Q2, here I have them differently, okay, 1S instead of S1, doesn't matter, and Q1 and Q2 end, right? Then I interpolate using the same basically duration. So basically, if I have the same duration, my S will be, I will have the same interpolator, the same velocity for the interpolation. But because I will have different values starting and ending here, different distances. Because I have the same duration, I will have different velocities for the joint. So the joints might not move at the same speed. Right? Another approach would be to use the same velocity, like say they're the same type of joint, so they can move equally fast, so I put them at the maximum velocity. So then I can have basically, for a shorter distance with the same velocity, I will have a shorter time duration. Right, so here I have the same velocity for the two joints, the slope is the same, but I have a different interpolator because I have different duration. Right, because I have different distance between the two. How do we expect the motion of the robot to be? I'm interpolating linearly the two joint coordinates. Right, so I will have like a line transitioning from Q S1 to QN1 and from QS2 to QN2. But what about the end effector? What do we expect? How do we expect it to move? Will it move on a line? Will it move in another way? Any intuition on that? Circular? Okay. Not on a line? Why not?
It will be moved as the same way in the same way as the arm. For example, if the arm moves linear, the end effector also will move. Or maybe
What do you mean the arm?
to be a little bit have a distortion to do the four. For example, if it's an arm like that, it will not be really.
Mm-hmm. So you say it will move like the arm. What do you mean when you say it will move like the arm?
For example, if more or less if the arm is moving linear, for example, it's based on the trajectory of the arm shortly.
Okay. Yeah, well that's why I'm asking, what is the trajectory of the arm? If I move at the joint level linearly, so I move the joints following a line, right? Do I expect the same behavior for the end effector? If yes, why? If not, why?
Because only the variation of the joint angles are linear.
Alright, and
The pose of the angles.
the pose of the end effector, what relationship does it have with the joint coordinates?
The same angular velocity, the same.
Is the end effector pose the position? Let's focus on the position.
And the factor is connected to the last piece, so technically it goes with it.
Alright, so
Doesn't
yeah,
have
both
a
motions
separate joint to
contribute.
to move the end effector, but you're going to move with the last piece.
Only with the last joint, you mean? What?
And it will mimic the movement.
Of the last joint only?
No, both will have a contribution.
Both will have contribution, right? But what kind of contribution? Do you remember the four kinematics? This basically is the relationship of Q to the end effector position and orientation, right? Is it a linear relationship or non-linear or what?
It is non-linear because it depends mostly on sine and cosine.
Right, exactly. So the position, you remember the angles were always inside cosine or sinuses, right? So it's a non-linear relationship. So if these move linearly, the end effector will not necessarily move on a line. Will for sure not move on a line, right? So then, yes, here we present the method to interpolate from one pose to the other. We have a smooth transition, but then what will happen at the end effector, it's definitely not going to be in line, unless these are prismatic joints, whatever. But in the general case where we have revolute and prismatic and whatnot, then it's not going to be a line. Let's see how it would look. So here I have like a small animation with two joints moving with the same duration. However, you can see both of them start and stop at the same time. But you also see like the end effector is not following a line, right? It's basically doing like a circular motion. Right. In the other case, we have one of the joints stopping first. because it has a sort of distance to. Now the second joint stopped, and now only the first one moves. So basically it does. And I think I have them one next to each other, so you can see basically what's the difference between the same velocity or the same duration of the two joints. All right. So this is the basics of how we apply interpolation to go from one pose to another. Not yet really trajectories, but it is somehow trajectories at the joint level. Before we move on to the end effector, let's see if there are any issues with this kind of interpolation, where basically linear interpolation going from QS to QT using a line. Can you imagine any problems with it? And maybe through these animations you can even
Maybe the torque,
What is it?
at the start, the torque of the motors will be higher because they have to start moving this standing mass.
all right, okay,
Yeah.
yes, and start moving in what way? It's the same problem also at the end, right?
Yeah, 'cause they have
To start moving immediately and then we have to stop moving immediately. Right, that's basically it. Is this what you want to say, or
No.
maybe say it too?
I was seeing that maybe we can enter in a non-defined case if T is equal to Ts.
If t is equal to ts,
We are going to enter in a divide by zero.
yes, but here we don't have any division by zero. Right, so this is just to calculate my QS, and if this is zero, it's the function is defined, so there's no problem. But good try.
Possibility like an issue with the safety because this interpolation could lead to some singularity cases, like a position of the arm that would be undesirable.
True, it can, because there's no guarantee here. We don't even think about pose or Jacobians or anything, right? So yeah, we could enter a singularity. However, since we're really controlling the joints, singularities don't come into play at all, in the sense that singularities is when we're trying to control the velocity of the end effector and we need to calculate the joint velocities to do that, right? As long as we're just controlling the joints, we don't have issues with singularity. Like we can always move the joints because they are just moving independently, right? The issue with singularities happens when we are like on controlling the end effector. But yeah, we could stop in a singularity position, and then I don't know, if we switch to another mode of control, maybe we'll have issues. What I want to go is what your colleague first said. Basically, since we have a linear interpolation, like on position, this is how the velocities will look like, right? I will have going from zero velocity to some velocity instantaneously, right? What will happen with acceleration? So this is the derivative of the position, right? So here I have zero, and at some point I have some velocity constant, and then I go back to zero. What about accelerations? What happens to acceleration? With the second derivative.
Goes from 0 to a value is
I basically have to differentiate this one, right? And here I have a discontinuity, which means my derivative, first of all, is not defined. But yeah, if in a real case, let's say we don't have a real discontinuity, but we have a very high increase in velocity in a very short amount of time, I will have an even higher increase in acceleration over a short period of time, and then the inverse at the end. I will have a very big drop in the acceleration. And acceleration is related to forces, right, from Newton, F equals ma. So when I have high accelerations, I will have very high forces as well, right? So what your colleague was saying, like, okay, in order to start the robot at the beginning, I need to have like very high torques, and in order to stop it again, I will have very high torques, which in real case, I mean, in theory it should be infinite. In real case, it will be very high, and that it will result in like vibrations and upstops. So how do we solve this? basically we want to have like what we call boundary conditions. So we don't want to have, let's keep this one, this one. We want to have some conditions for what should be the velocity and the acceleration at the beginning and at the end of the trajectory. Right? And in order to do that, basically I need the polynomial. So I define the interpolator not with this linear relationship here. This is a line, right? I didn't explicitly write it here, but I wrote it in the slides. Times t minus ts and times ts. So this is the same form, right? So instead of having a linear interpolator, I define a polynomial interpolator in this form. And I'll write it down because we need it. 4 plus c t3 plus d t2 plus d plus f. All right. And now I can impose certain what we call boundary conditions on this polynomial. So basically I can define what happens at the beginning and at the end of the polynomial, right? That's why it's boundary conditions, like, at the ends. Yeah, here I wrote that the time goes from 0 to t, just to keep things simple. Instead of going from ts to t end, we consider 0 when we start, and then this is the duration. Alright? So I can say what happens when time is 0. What do I want when time is 0? I want the interpolator to have value 0. And what happens when I'm at ending time? I want the interpolator to have value 1. As before, when t was t starting, or 0 in our case now, this was 0, and at the end was 1. So again, I want a transition from 0 to 1 on the interpolator. But now I want the derivatives of this. Basically, at the beginning and at the end. Let's put an equal here. And the second derivatives at the beginning and at the end to be equal to 0. Right, so that the velocity of the interpolator is 0 and the acceleration of the interpolator is 0 at the beginning and at the end. Right. If the interpolator has these conditions, then the resulting interpolation will also have the same conditions, right? Because this is the only thing that depends on time. So if the derivative of this is 0 when time is 0, then the derivative of this one will be 0 as well when time is 0. We can do it as an exercise and see that the derivatives will be the same. All right. Let's see, what is the derivative of this one? Sorry? A fourth order polynomial. Let's write it down. I should have written this down lower. But what is the derivative of this one? 5at at the power of 4 plus 4b t at the power of 3 plus c 3 c t at the power of 2 plus b 2b t plus e. Right, and the second derivative here because we need it. Will be 20 times a t at the power of 3 plus 12 b t squared plus 6 c t plus 2d. Correct? Here we have s of 0, 0, s of t equals to 1. Alright? Right. Now I have this 6 coefficients A, B, C, D, E, F, right? And in order to determine them, what do I do? I calculate the polynomial and its derivatives at the boundary conditions, right? So I say S of 0 equals to 0. What does this give me? If t is 0, sorry? F equals to 0. So if t is 0, all of these parts will be 0. So if S of 0 is 0, this gives me that F is 0, right? That's one equation. What do I get from S derivative of t? S derivative of 0 equals to 0. Again, 0, 0, 0, 0 equals to 0, so it means E equals to 0. And if I do the same thing here, D will also be equal to 0. Right? If I solve this for T, capital T, I can calculate equals to 1 with these three being 0. Basically, I calculate that these three are 0. I will have one equation. This one at capital T equals to 0 will give me something else. Not something that goes automatically to 0, but basically I will end up with three equations. Sorry, four. 1, 2, 3. Three equations, right? And I will have to figure out these three coefficients, A, B, C, because these we said they're 0. In the end, we end up with a system of linear equations. It's basically we can write like this. This is in the general form where I didn't set specifically these conditions to be equal to 0. I can give whatever values I want. We'll see later on why this might be useful. But yeah, if these boundary conditions are 0, then the first vector there will be 0 besides this one that will be 1. So it will be 0, 1, 0, 0, 0, 0. All right, for these conditions. So I can write this system of equations in this form, and I can solve it by basically inverting this matrix, multiplying it from the left, and then I can calculate A, B, C, D, E, F for whatever boundary conditions I want, like linear algebra. You following? All right. Good. As I said, when these boundary conditions meet, I already know CD DEF is equal to 0, and I can calculate the rest. Right. So if I use such an interpolator, now I have smoother transitions, right, where I can ensure that the derivatives at the beginning and at the end, the first and the second derivatives, will be 0. So here you see I have like a smooth transition from not moving to moving, right? And I will have an acceleration phase, a maximum velocity phase, and a deceleration phase. And here we can see also the velocity, the acceleration will have a similar form. All right, so how does this look like? If you pay attention to the animation, you'll see that the joints start moving slowly, and then they decelerate slowly. Right? That's the idea for polynomial interpolation. Good. But we're still at the joint level. Like we're still interpolating joint values, and this is useful for going from one pose to another, but there is nothing that tells me what happens in between. As we saw earlier, the robot might follow a circle, depends on what joints, what values we have, and so on. We have to calculate what would be the trajectory. And we can by using forward kinematics, but we cannot actually control it. What if I actually want to control the end effector trajectory? And say, for the simplest case, I want to follow a line again. So I'm here, I want to go there, but I want to make sure I follow a line. Right? I don't do whatever and I end up there, I just follow a line. How could we do that? Any ideas?
We have the equation of the line we want to follow, therefore we can sample it to get some values
Okay, and how do I calculate the intermediate points? So let me draw this a bit so that everybody can follow. What you're saying is, I'll erase this since I'm not gonna use this one anymore. Now I have a fancier. What you're saying is, if I have again my robot and I have a starting pose, right, and I have my end pose as well. Right? What are you saying is, take it step by step again. So I have a starting point, ending point, and
I draw the line.
I calculate a line between them, right?
And then, I don't know, I choose a step, like how many intermediary positions I want. And then for every position I calculate the inverse.
So basically, I take this trajectory and I can calculate. I'm not going to draw too many. Okay, some points on this line. I have to sample it. So what you're saying, yeah, I have to choose. Okay, what is the distance between the points I will take, right? Because, yeah. And then what will I do at every step? Solve the inverse kinematics. And here, top green one. Aikina. I don't know why I draw this like this, but anyway. Point is, I take the trajectory that I want to have, in this case a line, and I split it in intermediate points, and I calculate the inverse kinematics there. So this will give me some Q, and some Q, and some Q, and so on and so forth. And basically I will convert this line trajectory into joint trajectories by solving the inverse kinematics there. Because I need to go to joint trajectories, because that's what I'm controlling, right? In the end, I can only move the joints. So I cannot stay in the end effector trajectory. Right. How do I calculate this line? And let's take the simplest case first, it's just position. I don't care about orientation now. How do I calculate this line?
As a function of Q.
How do I calculate it as a function of Q?
Using the for loop.
We have been using Q, and now we're not using Q as a function. We are not defining Q as a function of time. We are defining position as a function of Q. Trajectory.
Position as a function of Q would be the forward kinematics, right?
Yeah.
We know that already. So how could we use forward kinematics?
So we know the end effector position now currently, or what exactly?
I know a starting pose, let's say where the robot is currently right now, okay, because that's my starting pose, and I have a target pose. And we say that I'm calculating a line, which is what your colleague suggested at least, calculating a line that connects these two poses, and we split it in. But how do I calculate this line? That's my question. So I have a starting pose, ending pose. Focus just on the positions for now. So what would be this? This would be the ending position, a vector of 3 elements. This would be the starting.
We can use Euclidean distance because the space is big.
To calculate the distance between them and do what with it?
Well, Euclidean distance isn't always a result of a straight line. And we know that
Yes.
there's the straight line distance, and for
Okay, but if I calculate the distance is what? Is it a vector? Is it a scalar? Is what? Distance is scalar, right?
Scale, yeah.
Just a number.
Yeah.
We can use Jacobian matrix to calculate. If we have initial position, we can find that the Jacobian on the end.
And
We will need also the rotation because the
This is just a first order polynomial that it has three variables like x, y, and z.
a first order polynomial.
Is that a polynomial? How is it called?
Yeah, function.
A function with three variables.
Yeah.
Alright.
And each variable is at the first power because we want
Okay. A multivariate function. No? Simpler. Simpler.
If you know the distance, can't we just, for example, if we take a sampling period of whatever, we can split the distance to, no, we can divide with the sampling period and we can add to the first point that distance and we get integer points from the start till finish.
Mm-hmm.
So we can.
So what you're saying is not the distance. I mean, wait, we know the distance. Okay, which is a number.
Yes.
Distance is a number, right? The whole length, right? And then where do we add that distance? Or we
To the
divide that
starting
distance to
point.
some.
Yes, to the
I don't know.
starting point, and we can this way we can create the points from the start to the finish.
But how do I add them? Because the distance is the points are vectors, or the distance is a scalar.
But we had to each point the scalar.
I add the same scalar to each point. It's
The
basically
direction.
scaling the vector, right?
Yes, we
So
need the
this-
direction.
So this position is basically a vector. And so if I add a number to all the three components of the vector, I'll just make it longer.
But if you know the direction, then
So I need to add basically what? This vector,
yes.
right? To this point. So I go here. And then this vector to this new vector, to the new point. Huh? So yeah, that's a approach. So I can calculate the whole distance, and then I need to calculate the direction as well. Normalize it. How do I calculate this direction? This vector basically. I know this one, and I know this one. This is these numbers. So this is, I know, P S. This is P end. So I need P S end. How do I calculate this if I know this thing?
PS minus
Sorry?
PS minus P.
P S minus P E.
plus.
I think it's P
PE
E
minus
minus P S. Yes. It's P E minus P S will give you that vector, which is let's see, P E minus P S. Okay, so this gives me this vector, right? I can normalize it, so I have a length, a unit length. E. So I calculate, I don't know, this vector with length 1, and then I can keep on adding, I don't know, I can multiply this with a, I don't know, a factor of 0.1, whatever, so I keep on adding this whole vector here. So I calculate basically the intermediate points. That's what you're saying. I think it would work. It's not what I had in
The
mind, but
problem is that this will work only in cases when the line is straight. Because
are there any cases where the line is not straight?
I mean, if you want to connect in a specific, I don't know, other, so not a straight line to points, then it wouldn't work. Because then
All right, but we're talking about straight lines now, right? You're talking about, I don't know, circular trajectory,
Yes.
right? Or I don't know, whatever other shape. Yes, sure. But we talk about lines. and all lines are straight, I think. All right, so this would work, I think. I don't see why it wouldn't. It's not what I had in mind, but it would work. It takes a bit of time, you know, to calculate this vector, but yeah, why not? But I have a other idea, and I'll explain you later why I think it's a little bit better. So let's move on because we don't have too much time. So what we can do is basically we can interpolate each one of these three elements together separately. Right? I can interpolate px starting to px ending independently, py starting and py ending, and pz starting, pz ending, and you know, here I will end up basically with some interpolation, or three interpolations, and the nice thing is that at any point in this interpolation, whatever three coordinates I take, I will be on the line. So these three vary linearly and independently from each other, right? And I will still, if the transition from x starting to ending is following a line, y is following a line, z following a line, then the transitions from the whole pose will also follow a line, right? Now basically I can interpolate these three from here to the end independently, and you know, whatever points will result at any time between 0 and capital T, it will also be on the line connecting these 2 points. Right. Now, why I'm saying that this might be a little bit better than using the vector approach is that I can use again my interpolator to go from the starting values to the ending values, right? And because I can use the interpolator, I can use the linear interpolator or the polynomial interpolator. So basically I can make the transition from this point to that point if I use the polynomial interpolator, make it a smooth transition, meaning have a zero velocity at the beginning, an acceleration, and at the end as well, right? Which, in order to do with the vectors, I would have to constantly modify the factor I said here that we have to multiply. So we basically make the first vector smaller, and slowly make them bigger, and then make sure we make them smaller again. But basically the vector approach would be the same with a linear interpolator. But having this form allows us to use the polynomial interpolator, so have like a smooth transition from here to there. Now, once we have the interpolators, I can sample them at certain points, as you said here very correctly. So I take that form for px, let's say for py and pz, and I sample it at certain for certain values of t from 0 to capital T. I can choose how dense this will be or how far away. Right? I can sample and take values for px, py, pz at these points in between, and then solve the inverse kinematics so that I calculate the joint coordinates at these points. All right. So this would be an animation where I have, the transition, as you see here, on 2 coordinates. And if you pay attention, it starts smoothly and accelerates and then decelerates. So now it accelerates, now it decelerates. Right? And how would this look like in graph? I'm not sure it's the same values, but anyway, the idea is the same. We have some starting values, ending values, and you see the smooth transition where velocities and accelerations are 0 at the beginning and at the end for each one of the 3 independently, right? And then I basically have to sample and solve the inverse kinematics at whatever sampling rate I choose. I can do it every second, I can do it every half a second, I can do it every half a millisecond, depends on the accuracy. If I solve the inverse kinematics, as I said, I will end up with joint values here. And since I will have a series of joint values, I will have basically joint trajectories, which would look like this. So this is the linear, the following a line trajectory at the Cartesian space. Cartesian space because I have the end effector coordinates with respect to a Cartesian frame, right? And this gets translated into joint space interpolation, where I take these poses at certain moments and I solve the inverse kinematics, so I calculate the joint coordinates for these joint poses. And if I connect these solutions together, I will end up basically with trajectories for my joints. So in order for the robot end effector to do this, the joint coordinates have to do this, right? For this example that I plotted here. Any questions? If you notice that when I have zero and effector velocities at the beginning and at the end, I also have zero and joint velocities at the beginning and at the end. Okay, here you see a little jump. That's basically, you cannot see it probably, but that's something 1 at the power of -5. So it's like this barely moves. It's like an artifact. That's the idea. Any questions?